All right, Calc kids, this is the second half of section 6.4, which was the fundamental theorem of calculus, um, taking definite integrals and evaluating those. So just kind of review from yesterday or the last video, when we were taking a function x cubed and going from 1 to 3, we're trying to find the area underneath of that curve. So we take the antiderivative, plug the top number in, subtract what we get when we put the bottom number in. Okay, now this note down here is the next part that I want to come to and talk about. And basically it takes into consideration the c part, right? Because when we were doing antiderivatives, okay, the antiderivatives really, has to have that plus c at the end of it, right? So like when you're taking the antiderivative of, let's say, like 2x, right? The antiderivative of 2x would be x squared, like basically gets you back to the original function, right? The derivative of x squared is 2x, but it actually should be x squared plus c, right? Because that c just drops off when you take the derivative, right? So where did the plus c go? Like, why haven't we been using plus c in this top part, when we were evaluating those, okay? Well, really what will happen is, when the c really still exists there. When you are taking the antiderivative of f of x, it is the antiderivative of plus c, and then you would plug in your numbers b and a, okay? When you plug b in, okay, b is going to get plugged into the function, then you still have plus c on the end here. And then you plug a into the function, and you have another plus c there, okay? And that constant should be the same number, right? Like it would be x squared plus, let's say, 4, and I would plug my first number into here, and I would subtract what I get when I plug in x squared plus 4, like the second number, right? Okay, so let's say that this was my antiderivative, and I'm plugging my top number in for x, and I'm plugging my top number in for x here, or my bottom number in for x here, and I would get an answer. But what's going to happen is you see the 4 minus the 4, and really that c just crosses out, okay? So when you are doing a definite integral, and a definite integral means that you have your limits, okay? So this is definite integral, meaning I have my limits of integration from a to b, or I have numbers here, okay? And indefinite integrals when I don't have those limits, so I'm just evaluating, but a definite integral will not have a plus c on the end of it. Okay, an indefinite integral will, okay, because you're not plugging those numbers in, and that c doesn't just go away. But this is kind of why the c is gone, and we haven't been talking about c lately, okay, because so he is still there, but he basically cancels out when we plug numbers in, okay? All right, last two concepts are the mean value theorem and the average value theorem, and they both go together. So the mean value theorem says this, okay, let's say that here's my y-axis and here's my x-axis, and this is what my curve looks like. And I'm trying to find the area underneath of that curve, okay? So from A to B, okay? They have these labeled as A and B right here, okay? So the area underneath of that curve would be like this orange part right here, okay? And I would find the area of that by taking the antiderivative of the function, whatever this function f of x would be labeled as, okay? And then I would plug in b and a after I take the antiderivative and do that. Okay, what they're saying with the mean value theorem is that there exists a c somewhere between a and b, so that when I go up to c, I can basically make a box, and the area underneath of that box, maybe I should get some different color. My purple's kind of pooping out on me. Okay. The area underneath of this box will be the same as the area of what was underneath of that curve. Basically, they're like taking this area that's up top here and like shoving it down under there, okay? And they're saying that this c value will end up making a rectangle out of a really ugly curvy function, and those two areas will be the same, okay? So to give you another example, let's say I had like the curve of, I don't know, the square root of x, which kind of looks like this, right? Okay. If I'm looking at let's say from here to here, if I'm looking at that area from A to B, okay, of the square root of x, and I want to know the area underneath of this curve, what I might do is I might drop my C probably a little bit closer to A, because as soon as I section that off and make this box right here, this area, even though it's longer, okay, kind of is made up over here. So it's not necessarily that C will be exactly between A and B, but just kind of wherever it should be located in order for the above part to kind of make up the below part that's not there, okay? So you're trying to find a C basically so that this rectangle will have the same area as what the area underneath of the curve would be. It's like taking a curve and trying to make a rectangle out of it, because a rectangle is an easier shape than a curve, okay? So on the back side, the average value is actually finding that C, okay? So average value equals the C, which is the height of the rectangle with same area under curve. So they're basically like saying, how tall does your rectangle have to be in order for that rectangle to have the same area as what's underneath of the curve? Okay, so they kind of go together. The average value is actually finding that value of C. The mean value theorem is just saying, hey, there exists a C so that this happens, okay? And the formula for doing this is the same, this part here, this from A to B of f of x, this is just like finding the antiderivative, okay? Just like we've normally been doing, but then the height of the box will be determined by 1 over b minus a, okay? So that will tell us what our average value will be, okay? So it says find the average value. Basically find the height of the box that is necessary for this box to have the same area as what's underneath of my curve here. So if I section this off, I'm looking for this area here to match this box right here, okay? Because I want to like switch it to be a box now, because boxes have nicer areas than what's under curves, okay? So I'm really looking at finding the height, or how tall this box has to be. Okay, that's what I'm doing by finding the average value, okay? All right, so what I'm going to do is I'm going to set this up, and I'm going in the interval from 1 to 4. Let me get this on fuzzy. Interval from 1 to 4. Okay, formula says I need to do 1 over b minus a, and then I do the integral from a to b of, I'm just going to go ahead and plot my function in here, 3x squared minus 2x dx. Okay, this is the function that I'm doing for f of x. So I've basically just taken this formula, rewritten him down here, and we're going to find what the average value will be, okay? So now we have to figure out what A is and what B is, okay? A is going to be where I'm starting at, B is where I'm ending at, so 1 and 4 is going to be the values. And so I do 1 over 4 minus 1, and then I'm doing the integral from 1 to 4 of this function, 3x squared minus 2x dx, and at the end I'm going to multiply him by this piece out in front here. Okay, this is going to tell me how tall my box needs to be. All right, so let's do the inside part here first. So we need to take the antiderivative of 3x squared minus 2x. Okay, so we can do the 1 over n plus 1 x to the n plus 1. So 3 over n would be 2. So I have 2 plus 1 x to the 2 plus 1 power, okay? So that was going to be 3 over 3, which is just 1x cubed, okay? If I look at 1x cubed, is the derivative 3x squared? Yes, so that's correct. Then I have minus 2 over n plus 1, okay? N in this case is 1, so I have 1 plus 1, x to the 1 plus 1. Okay, so this is 2 over 2, or just 1 x squared. Okay, you might be able to do that in your head, and that is totally fine. I just wrote out all the steps if you need to see that. Check real quick, negative 1x squared is the derivative 2x, you betcha. Okay, and I'm going to use that notation, those little brackety things, and I need to plug 1 and 4 in. Okay, so plugging 4 in first, I basically have 4x cubed. I'm going to get rid of the 1, I don't really need the 1 in there. Okay, minus 4 squared. So 4 cubed minus 4 squared. minus, so this part, minus what I get when I plug 1 in. So 1 cubed minus 1 squared. Okay, and I need to figure out what that is, all right? So 4 cubed is 4 times 4 times 4, which I think is 64. 64 minus 16, okay? And then I have 1 cubed is 1 minus 1. Well, really, 1 minus 1 is going to make this entire thing go away, because 1 minus 1 is 0. So I'm really just looking at 64 minus 16, which is 48, okay? Now, I'm trying to find the height of that box, right? So does that mean that my box is 48 units tall? Not quite. That was just this part. I need to then do the 1 over 4 minus 1, or 1/3. 4 minus 1 is 1/3 times 48, and 1/3 of 48 is actually 16. So the height of my box will need to be 16 units tall in order for that box to have the same area as the curve, okay? So this is called the average value. We have found the average value, and that is going to be 16, okay? All right, that is all I have for you.